If you're sufficiently interested in mathematics, chemistry, or even physics, odds are that you've heard about group theory. To put it simply, group theory studies symmetries of objects, both concrete and abstract. However, despite its wide applicability, group theory remains largely inaccessible to most enthusiasts as it is typically taught during the third year of an undergraduate degree. Here is our attempt to change this and build up to some truly deep results in a way that, hopefully, feels natural. But before we really begin this journey, let's just hone our problem-solving skills by looking at a fun little permutation problem that is related to the symmetric groups. So, we want to find the smallest n for which there exists a permutation satisfying some property. Before going into the specifics of the question, let's discuss what a permutation actually is. Well, it's just a rearrangement. Let's say that we have 5 objects and a permutation that acts on them as follows. Here's how we can view this as a function. Let's leave a copy of our objects above and apply our permutation again. Since dot 3 is below the duplicate dot 1, we can say that f of 3 equals 1. Similarly, we can also see that f of 4 equals 2, f of 1 equals 3, and so on. Essentially, f of something is where that something will be after one application of the permutation. Likewise, f of something tells us where that something will be after 2 applications of the permutation, and so on. We can see that something interesting just happened. All of the points are back in their original locations. When a function maps everything back to where it was initially, we say that it is the identity function. Now that we know all of that jargon, let's take a good look at the problem statement again. For the purposes of this problem, we will arrange our points in a circle instead of on a line for reasons that will soon become apparent. To get some intuition for this new view and to understand the f to the 1000 condition in the problem statement, let's look at some examples of permutations. Let's keep track of how many times we've applied our permutation in the top right corner. Here's one that moves every point by 1. In this permutation, f to the 1000 equals the identity, and applying the permutation fewer than 1000 times doesn't result in the identity. This means that the permutation satisfies the f to the 1000 condition, even though it may not have the smallest value of n. Here's a similar permutation with 4 points. Even though f to the 1000 is the identity, it does not satisfy the f to the 1000 condition since it results in the identity permutation after only 4 applications of the permutation instead of 1000. Now, let's look at a permutation of n points that satisfies the conditions of the problem. This is a bit cluttered. For now, let's just track the first dot and ignore the others. We can call the path that one takes its cycle. Observe that since f to the 1000 is the identity, every point must be in some cycle. Now that we've defined cycles, let's play around with them. Suppose that we have 2 points A and B in different cycles. Since this looks a bit confusing, let's bring a copy of these points out into their own circles and rearrange them to untangle the arrows. Observe that all the dots in the 2 cycles will go back to their original positions when the number of times that we have applied our permutation is a multiple of 4 and 10, the cycle lengths. Since 20 is the least common multiple of the cycle lengths, all the points in the two cycles first return to their initial locations after we apply our permutation 20 times. Since every point must be in a cycle, this original circle can be broken apart into m different cycles. Let's call the length of the ith cycle c sub I. Like before, we have that the identity first appears after LCM C1 to Cm applications of the permutation. The problem tells us that 1000 is the smallest number for which f to the something is the identity. However, we know that the LCM of the cycle lengths also has that same property. This means that 1000 equals the LCM. Also, since all the points are in a cycle and the cycle lengths are equal to the number of points in the cycle, we get that n equals the sum of the cycle lengths. Before wrestling with our equations, let's go over a concrete example of computing the lowest common multiple. Say we have these four numbers and we want to find their LCM. One way to do this is as follows. First, we find the prime factorization of each number. To make the process neater and clearer, let's add in the exponents equaling 1. For better alignment, let's rewrite the numbers like so, keeping in mind that anything to the 0th power is 1. Next, we pick the numbers with the maximum exponents from each of the columns and multiply them together to get the LCM. Now that we've gotten that out of the way, let's go back to our two equations. We need to find cycle lengths whose LCM is 1000 while trying to minimize their sum. So let's try out some examples. Let's start simple with one cycle whose length is 1000. This gives us n equals 1000. Next, let's have two cycles with lengths 2 cubed and 5 cubed. This is enough to satisfy the LCM condition. The resulting sum of the cycle lengths seems quite small, at least compared to our last attempt. Let's run with this and try to prove that the sum of the cycle lengths is always at least 133. The first equation tells us that 2 cubed times 5 cubed is a multiple of every cycle length, which means that any cycle length ci equals 2 to the ai times 5 to the bi for some ai and bi between 0 and 3 inclusive. Let's get rid of everything with an exponent of 0 since multiplying by 1 doesn't change anything. Suppose that all these are 0. We know that whenever we have two integers greater than 1, their sum is less than or equal to their product. This gives us the following lower bounds for each of our products. Since we want to bound the sum of the cycle lengths, let's add up both sides. Next, let's also group the 2's and the 5's together. To satisfy the LCM condition, one of these must be a 2 cubed, which means that this part is at least 2 cubed. Similarly, this part must be at least 5 cubed. Therefore, the entire sum is bounded below by 2 cubed plus 5 cubed. Let's now collapse this inequality. Recall that the sum of the cycle lengths is n. So this becomes... That leaves us with this rather simple inequality. Hence, for any valid permutation, n must be at least 133. So, all that remains is finding a valid permutation on 133 points. So, here are our dots. We know that we have two cycles, one of length 2 cubed and the other of length 5 cubed. Let's arrange these points accordingly. Now, one possible permutation simply rotates both of these cycles like so. Since we found a permutation with 133 points, ours must have the minimal n, so our desired minimum is 133. To put it simply,